In this video, I want to show you how to use the Hungarian algorithm. And what is it used for? You see a cost matrix here. You are already familiar with that from our last video. It's on page 378 in your textbook. So it's a cost matrix, and it displays the time and each employee takes to complete a task on each machine. And we want to use this cost matrix to determine the best assignment of employee to machine, so that the overall time taken to complete the task is minimized. And we can do that by using the Hungarian algorithm. So this involves a few steps, and there we go. Step 1. So step 1 is that we subtract the lowest value in each row from every value in that row. So have a look at this cost matrix. The lowest value here for the first one is a 30. So in the second row, the lowest value is a 30. In the third row, the lowest value is a 30. In the fourth row, it's a 20. Okay, so for each row, what I'm going to do, I subtract the lowest value in each row from every value in that row. Okay, so 30 was the lowest here. So I have 30 minus 30, that's going to give me a 0. I have 40 minus 30, that's going to give me 10. 50, subtract 30, that's a 20. And 60, subtract 30, that is a 30. Second row, the lowest value was 30 as well. 70 minus 30 is 40. 30 minus 30 gives me a 0. And 40 minus 30 gives me 10. 70 minus 30 gives me 40. 60 minus 30, so lowest value again is 30. Subtracted, it gives me 30. 50 minus 30. Gosh, lots of 30s here is a 20. 60 minus 30 is a 30. And 30 minus 30 is a 20. Good. So last row to go. 20 minus 20. Lowest value here is a 20. So I subtract that. It's going to give me 0. 80 minus 20 is going to give me 60. 50 minus 20 is going to give me a 30. And 70 minus 20 is a 50. So now that is done. And we have to have a look at step 2. If the minimum number of lines required to cover all the zeros in the table is equal to the number of allocations to be made, jump to step 6, otherwise continue to step 3. Okay, what does that mean? Minimum number of lines required to cover all the zeros. Okay, well, let's draw some lines here to cover the zeros. Okay, so we cover a 0 if we draw a line here. Cover 2 zeros actually. If we draw another line here, we're gonna have that 0 covered, and we can draw another line here. Okay, 3 lines. So the minimum number of lines required to cover all zeros, minimum number in this case is 3. If that is equal to the number of allocations to be made, jump to step 6. So how many allocations do we have to make? So we have 4 people, 4 machines. Well, that is 4 allocations. So 3 is not equal to 4. Therefore, we cannot jump to step 6. Otherwise, continue to step 3. Okay, step 3. Good. Oh, I've done already my lines in the other step. Should have done it down here. Oops. Well, anyhow, the outcome is the same. Good. Step 3. If a column does not contain a 0, subtract the lowest value in that column from every value in that column. So this is the column here, which does not contain a 0. What are we supposed to do? We subtract the lowest value in that column, which is a 10, from every value in that column. Okay, and so I've got that prepared already here. I have 20 minus 10. That is 10. 10 minus 10. Ooh, another 0. 30 minus 10 is 20. 30 minus 10, another 20. Good. We have another 0 now, so let's see what we do. If the minimum number of lines required to cover all the zeros in the table is equal to the number of allocations, so we know that already, jump to step 6, otherwise continue to step 5a. Okay, so we need to cover that table. We need to cover the zeros in that table with lines. Good. Do that. I can draw a line here and have 2 zeros covered. I can draw a line here of 1 0. Oh, 2 zeros covered, and there's another 0 here. Good. All zeros covered, but 3 lines. So that means we can still not jump to step 6. We need to continue to step 5a. Okay, step 5a. Add the smallest uncovered value to any value that is covered by 2 lines. Okay, have a look at the uncovered values. 10, 10, 20, 20, 60, 20. The smallest of those is a 10. What do we need to do? We need to subtract that from all, add the smallest uncovered, we need to add that to any value that is covered by 2 lines. Okay. The 10 needs to be added to the values that's covered by 2 lines. So I need to add a 10 to that 40 and a 10 to that 40. And now what do? I subtract the smallest uncovered value from all the uncovered values. Okay, so the smallest uncovered value is still the 10. And I need to subtract it from here and 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 from here. Okay, that's like 2 steps in one. I have that prepared already here. 40 plus 10 is 50. And 10 minus 10 gives a 0 over here and a 0 over there. Okay, 40 plus 10 is still 50. And I subtract zeros from those 10s from those 20s, so I'm gonna get 10s. And I subtract 10s from those values, so 60 minus 10 is 50. 20 minus 10 is 10. Now what? 5b. Repeat step 4. Okay, step 4. If the minimum number of lines, okay, so we need to draw our lines again. Take my red pen. 1 line here. And I can draw another line here. Oh, and I can draw another line here. And I've got 2 new zeros there. So that means I would need another line, which gives me a total of 4 lines. But I need to make 4 allocations. So this time the number is equal. So I jump to step, oh, done it already. I jump to step 6, finally. What's step 6? We draw a directed bipartite graph with an edge for every 0 value in the table. Okay, so an edge for every 0 value in the table. So Wendy and A is gonna have an edge. Right? Okay, Wendy, and there's another 0 to B. So we're gonna draw also an edge from Wendy to B. And there's another 0 to C. So we also draw an edge from Wendy to C. Good, so now, next one is Xenophon. Xenophon, try to display both, has a 0 to B and a 0 to C, so he's going to B and to C. Okay, over there and over to C. Yolanda has only 0 to D. Oh. And then what's left? Zelda. Zelda has a 0 to A, so Zelda's going to A. Good. There we go. bipartite graph is done. We draw a directed bipartite graph with an edge for every 0 value in the table. Good. Step 7. Now we have to make the allocations for that. And therefore we need to have a look at our initial cost matrix, and we see that Wendy, oh well, let's start with those who can't do anything else. So Yolanda goes to D, and Yolanda needs 30 minutes to do D. So that's the 30. And Zelda goes to A, and there's no other option. That's 20 minutes. Okay, but if Zelda goes to A, nobody else has to go there. So we can delete this if we wanna. And now we have 2 people, Wendy and Xenophon, and they can both operate B and C. So what we have to do now is have a look at the values. So if Wendy operates machine B, it's going to take 40 minutes. Hang on, so we've got the 30, we've got the 20. So if Wendy operates B, we have 40. And that means Xenophon then needs to operate C, and that would be 40 minutes. So that is the one option. The other option is that Wendy operates machine C. Wendy operating machine C would take 50 minutes, and then that would mean that Xenophon needs to operate machine B, and that would take 30 minutes. So we have 2 options here, but have a look. They both give the same result. That's 50, that's 50, and that's an 80, and that's an 80. So both time, 50 plus 80, we're gonna have 130 minutes. Right? So we can choose where there is no difference in the minimum allocation, in the minimum cost, but only one person needs to operate one machine here from Wendy and Xenophon. So I can say Wendy is supposed to do C, well then Xenophon is supposed to do B. Right? Doesn't make a difference. So try out this Hungarian algorithm in exercise 9b, questions 6 to 11.